In this section, we will study about the difference equation, and that will represent the discrete system. Let's starting with a continuous system first. In a continuous system, xt is a continuous input, and ht is the impulse response of the system, and yt is the output. It's the same in the discrete system. xn is the input sequence, hn is the impulse response of the discrete system, and yn is the output. In a continuous system, usually it can be expressed by the differential equations. In a continuous system, it's given looks like this one. Output weighting factor is a, and differentiation for the output is left hand side, this part, and the right hand side is weighting factor is b, and taking derivative for the input sequence. So usually continuous system are expressed by these differential equations. To get the transfer function of this system, we are taking the Laplace transform. In the Laplace domain, differentiation can be time derivative can be expressed by the s to the n. So it's a polynomial equation for the s. So the left hand side can be expressed in this polynomial equation, and ys is common factor in the Laplace domain. As similarly, input signal for the right hand side, that is also converted into Laplace domain. It's given like this polynomial, and xs is the Laplace transform of the xt. The transfer function is the ratio between the output y to the x. So by taking the ratio, then that the right hand side polynomial becomes a numerator, and left hand side, this polynomial, even denominator. Numerator will give the zeros. Denominator will give a poles, given in this way. So this transfer function characterizes the system, and by taking inverse Laplace transform, it will give impulse response of the system. Corresponding discrete system, you can see here, that can be expressed by the difference equation. In the discrete domain, the sampling time is fixed, so only sequence is given. That's why in the discrete system is described by difference equation. So time difference. So this one is a weighted sum of the past output, okay, and this one is a weighted sum of past input. So a and b is weighting factor for output and input terms. We study about the DTFT. By taking the DTFT for both sides, discrete time Fourier transform, we know that the time shifting. So if xn DTFT is x e to the j omega, then x n minus m0 will give e to the minus j omega m0 times x e to the j omega. So we talk about the time shifting property. Okay, if there is a time shifting, then this term will come out. This is time shifting versions of that. So that's why these terms are expressed in this way. This means the time shifting factor. So this is time shifting, and this is weighting factor, and y e to j omega is a DTFT of the yn. It's similarly the input sequence also expressed in the time shifted version, and this is weighting factor, and xn DTFT is x e to the j omega. The transfer function also the same as y to the x ratio. Then it will give the polynomial equation. In this rational function, the numerator polynomial will give the zeros, and the denominator will give the poles. It's the same. Okay. In case of the limited data, it means that we have limited data, the window size. So we have L data, then WL is expressed in this way. This means that the frequency step is 2 pi divided by number of data, or length of the window size. Okay. In case of DTFT, we have only limited window size. That's this one. And YK is the DTFT of the YN, and this one is DTFT of XN, and this one expressed the time delay factor. So delay factor, at this moment, this is delay factor. Okay. K is the spectral index. At this moment, N is the delay terms. Okay, at here it's the same. Don't be confused. This N, this is the sequence index, but this one is this index. Okay, the memory element. How many flip-flops exist? Okay, feedback term and the input terms, like that. So in the transfer function, the ratio between y to the x will give the similar polynomial equation are given in this way. So we talk about the transfer function for the discrete system. In the discrete system, system can be described by the difference equation, and by taking the DTFT or TFT, we can figure out the transfer function of that. Here shows two discrete system examples. The one is finite impulse response system. It's called FIR system. The other one is the infinite impulse response system. It is IIR system. The first one at here, the FIR system has a finite duration impulse response. It means that the impulse response is disappeared in a certain time period. But in case of infinite impulse response system, the impulse response will lasting over time. It didn't disappear. It exists over time. The system characteristic difference between these two systems is that in case of FIR system, it didn't have any feedback. So output is just the weighted sum of input sequence. But in the IIR system has a feedback terms. Here shows that the output Y is tapped out at here and feedback to the input side and then summing up. So this path is called feedback. If there is a feedback, then there exists the poles exist. But if there is no feedback, they have only zeros. This kind of system didn't have a pole. Let's look at a little bit detail. Here it shows that the D is D flip-flop. This is the same. So it's a delay element, 1 clock delay. So if input is applied and the clock is ticking, then that is stored at here. That's the previous data. Another data will come out. So this one seems like a shift register. So D means that the delay element in physical device is D flip-flop. Okay. Here shows that the structure, the input is applied here, and the previous data and 2 times previous data is stored at here. So there's a 3-point data exists here. So current input xn is current input. This one is a previous data. So xn is applied, then weighting factor is 1. That is added to the output. And previous data has a weighting factor is 0.5. That is added also. And the 2 times previous one also has a weighting factor minus 0.25. That is added. Then that becomes the output. So this output expressed by this way. Output is current input. Weighting factor is 1. That's this terms. And the previous data, 1 time previous data, weighting factor is 0.5. That's the distance. And 2 times previous data has weighting factors minus 0.25. So system can be expressed in these difference equations. We would like to find out the impulse response. To find out the impulse response, we need to apply impulse to the input. So xn now becomes the impulse response. Then the output becomes the impulse response of the. Okay, so this is the story. Input. If input is impulse, then output becomes the impulse response. The impulse system is if n equals 0, then that is 1. Okay, I would like to plot impulse input. -1, if n is -1, -2, whatever, everything is 0. So 1, 2, also 0, like that. This is the input impulse. Okay, so if I can express this one in this way, you know that Hn, at this moment we are taking Xn input as a impulse, so we can rewrite this equation in this way. At this moment, output becomes the impulse response, so Yn is Hn, so that's this one, and Xn is delta n, and the weighting factor 0.5 times delta n minus 1, and minus 0.25 times delta n minus 2. Okay, so this is the impulse response behavior. Let's consider that n is less than 0, so there is no impulse exist. So input is 0. It means that n is less than 0, all these terms are 0. And if n is less than 0. What about n equal 0? Then n equals 0, this is not 1. But this terms, delta minus 1, delta minus 2 is 0. So this is 1. That's why H0 is 1. What about n equal 1? If n equal 1, then this becomes 0. And this one is non-zero, 0.5. Because if n is 1, then delta 0 is a 1. So that's why it's 0.5. But this one is 0. So that's a 0.5. And what if n is 2? If n is 2, delta 2 is 0, and delta 1 is 0, but this one is delta 0. So if n is 2, then this is minus 0.25. Okay? If n is greater than or equal to 3, then all those values are 0. So this one is the impulse response. What if I plot that one over the index n? Let this point is n equals 0. In case of n equals 0, it is 1. Okay, so I would like to plot Hn. So if n is 1, it's 0.5. And n is 2, that is minus 0.25. All the other terms are 0. Okay, this is the impulse response. You can see here that the impulse only exists on this 3 point, 0, 1, and 2. So only n is in this range is non-zero. So that's why it is called finite impulse response. And here you can see the weighting factor 1.5 and minus 0.25. That's the impulse response. So that is the impulse response. You can see here. This weighting factor by itself is impulse response. I would like to take in the DTFT of the impulse response. You know that Hn is given like that. Then we can find out the DTFT by taking these summations. But at here, n is only non-zero in case of 0, 1, 2. Except this value, Hn is 0. So in fact, the summation taken from minus infinity to infinity, Hn is non-zero only in this part. So we need only 3 summation is enough to find out the DTFT. So in case n equals 0, H0 is 1, and e to the j omega n is 1. So that's this part. And if n is 1, Hn is 0.5, and n is 1, e to the minus j omega. Okay, this is it. And if n is 2, then Hn, H2 is minus 0.25, and n equal 2, then that's the minus j 2 omega. So this is it. So this is DTFT of the system. The output will be given as a convolution between input and impulse response. By taking convolution, Hn is only non-zero, 0, 1, and 2. So that's why input is expressed in this way. You need to carefully compare this system diagram and how we're gonna find out the impulse response of that one, and also how to taking the DTFT, and what if we taking the impulse response by taking the convolution, we can find out the output in these equations, how we can express that one. The next example is impulse, the infinite impulse response system. So at here that the output is tapped back to the input, so we can express y1 in this way. Xn and 0.5 of the previous output will becomes the next output. So next output is current input plus 0.5 previous output. Okay, this is it. So that is expressed in here, and it also expressed in this way in the difference equation. Okay, then what is the impulse response of this one? We assume that the input is impulse. Okay, if n is less than 0, if xn is 0, so obviously output is 0. Okay, n equals 0, then I can rewrite this one, h n equal delta n plus 0.5 hn minus 1. If n is less than 0, hn is 0. If n equals 0 cases, this is 1, but this one is 0, so that's the 1. If n is 2, n is 1, then delta n is 0, but h0 is 1, so that's why it is 0.5. If n is 2, then this is 0, but h1 is 0.5, so we take the half of that one, 0.25, like that. Now consider these equations. In these equations, if n equals 0, then this means that the h0 is delta 0, so that is 1. And if n is larger than 1, greater than 1, then delta n is 0, so hn is 0.5, that is 1.5, so I'd like to that one. 1.5 times hn minus 1. This sequence is just a power series, so in general terms we'll give like this way. It's a power series. The ratio is 1.5. Okay, so we get the impulse response of this one. So if I plot that one, this is n. If n is 0, then this is 1. So if less than 0, minus 1 and minus 2, all the way 0. This is 0, n is 0, n is 1, 2, and in these sequences, it is 1.5, 1/4, and like that. It is 0.5, 0.25. It is decreasing in this way. Even though this is decreasing as this pattern, it is approaching to the 0 like that, but still there is a response that remain over time. So that's why it is called impulse, the infinite impulse response. We would like to take a DTFT of this system. We know that the exponential function DTFT has these shapes, or we can taking the DTFT for the time shifting version. So this is y e to j omega, and minus 0.5 times, this is one time shifting, that is this terms. Okay, so okay, here is typo, minus 1, so one time shifting, negative direction. So we can find out the transfer function by use of these differentiation, or we know that the exponential function has these shapes of the DTFT output.